Yeah.
It's not.
It's
Them ones are
Okay, it's working.
where some of the area will be maybe 15 states.
Thank you.
Okay, I will let's just so but this like do you need actual the structure?
This is so.
Yes, I'll say something.
Okay.
So welcome Reinhard Laubenbacher from the University of Connecticut.
Great, thank you. Thanks very much for asking me to come down here. As I said, I've never been in this building, so this is my chance to come here. So what I thought I would do is give you a fairly high-level overview of some of the mathematical things that we've been doing essentially since I got into this field maybe 17, 18 years ago, 15 years ago, some such thing. And I will say relatively little about the biology. I'm happy to, of course, answer whatever questions you might have in this respect. So the basic mathematical problem that we look at in different guises and different forms is a very simple one. You have a finite set, and you want to think of this set as sort of the collection of states that your system might be able to take on. We'll specialize that in a little bit. And you have a function that takes one of these states and transforms it into another state. So you have a function from a finite set to itself. And as you iterate this function, you get a dynamical system. You can think of this as a dynamical system, which you can describe by a finite graph, a state space graph that has as vertices all the elements of x and has edges that come by from applying this function to itself. And the fundamental problem is I describe to you what f does, and you tell me something about the state space. Okay, so that's no different really from what people do that study, say, ODEs. They give you a system of ODEs, you tell me about the dynamics just from the structure. And of course, in general, you can say absolutely nothing. There are no mathematical tools that you could use other than your bare hands. And there is essentially no information that you can extract from it. So where do these finite sets come from? Here's an example of a paper we published a couple of years ago. This represents sort of a gene regulatory metabolic network in a fungus. The fungus is Aspergillus fumigatus, which does bad things to you if you're immunocompromised. And this is a network that describes the regulation of iron uptake and iron storage inside of this fungus. So the different nodes in this graph represent different molecules, and edges in there represent different regulatory relationships, so causal interactions. And you'll see if you look carefully, there are two types of edges that have regular arrows and then ones that have these blunt arrows. And the ones with regular edges, they are activators, meaning if you know that the source goes up, and you know that at the tip goes up as well, and otherwise. So this will, and each of these can have different states. In our case, we look at discrete states. So one of these could be low or high, or low, medium, high, or different nodes might have different states, and the collection of states together, that's your set X. And then you have this set X, this system evolve over time, that gives you, in this case, your function. And you would like to know, for example, what are the different phenotypes that this fungus is capable from the point of view of iron synthesis. Right? So there would be some information you might want to extract out of this function. So this is sort of the other graph that goes with it. It's the graph of regulatory relationships, right? So if you take this graph and you abstract it, you get a graph with vertices x1 through xn, and then you have edges that in this case come with weights, plus or minus 1, depending on activation or inhibition. So this graph is part of the description of the function f. And so in part it is information in this graph that you want to use to say something about the state space graph. And then, of course, since it's a dynamical system, you want to build dynamics on top of it, so you can do this in a number of ways. Many people put ODEs on there. So most differential equations models of systems of this sort also start with a graph. And the graph, the edges typically have weights that represent parameters. But you could do a number of different things. We use a number of different models. We use stochastic models, we use ODEs, we use Boolean networks, generalized Boolean networks. So you asked me a minute ago about, do we use something other than Boolean states 0, 1? So this here, some of these nodes have 2 states, some have 3 states, depending on what they do.
Is there an approach of making a choice of what kind of models you will consider?
Yeah, that's right. So depending on what you want to know, you will need to do different kinds of models. So for example, the project that I mentioned a minute ago before we started has to do with injury to tissue based on blood clots. So their time is very, very important. The longer your tissue is deprived of oxygen, the more damage you get, you get different features. And so a model like a Boolean network would be not a good model to use because you don't have a good sense of time. You need to use differential equations or some other kind of model that has explicit time built into it. Okay. But what I want to talk about today has all to do with sort of Boolean or generalized Boolean. And so there, the basic problem is you have a function that goes, you have a set x that's your states, in this case it's 0, 1, and you have a function that takes binary strings and transforms them into binary strings. So there, the problem is the same. I tell you what the function does, you tell me what the state space graph looks like. Except I've gained absolutely nothing, because any function is a Boolean function. I can take any set function from x to the n to x, and I can write it as a Boolean function. So the problem has not been simplified. So to just iterate, the key problem is you want information about the state space graph from the structure. So looking at it from a biological point of view, the structure of the model is essentially the genotype of the system, and the dynamics is the phenotype of the system. And that's, of course, one of the central problems in biology. You go from the genotype to the phenotype. You want to predict what the phenotype is based on the genotype. Right? You want to sequence a patient's DNA and tell this patient, you will develop diabetes by the age of 50. And we will start treating you by the age of 40. Simplistically speaking. So to make this problem at all tractable, one needs to do 2 things. One, you need to impose some conditions on your functions. Otherwise, you're talking just about set functions. And the second one is you need to have some sort of a mathematical framework that you can use as tools, because whether it's Boolean functions or whether it's set functions, you have no mathematical tools to do this, other than taking a function and exhaustively iterating. And then, of course, once the dimension n gets large enough, it's a hopeless endeavor. So let me start with the second one first, the mathematical framework. And that is something we started pretty early on when I got into this field. It's the paper that you just mentioned earlier. the problem was we have a collection of measurements, system-level measurements. So in this case, we measure all the genes in the system that you're interested in. You have a time course of these genes. You would like to infer a model of that system just from the data. Because, of course, the way models are typically built is you have a collection of detailed experiments that elucidate for you the biology. What relates to what? Like you take this gene, you block its effect, you see something else goes down, you say, oh, this gene must regulate that gene. And that's, of course, not scalable by any means. And that was the impetus for systems biology and new approaches when you had these so-called omics data. Genomics, proteomics, metabolomics, you could take system-level measurements. You could measure the expression of all the genes in a cell, all the proteins in a cell. Right? That makes this approach feasible. And so here we took the approach, well, can we infer Boolean network models from time courses of data? And we used the observation that if you take any function on a finite field, or any function, so in this case Boolean, we take the field with two elements, F2, and you have a Cartesian product of the field F2 with itself, and you have a function from that field from that Cartesian product into the field, it can be written as a polynomial, uniquely with square freedom numbers. And so Boolean networks are just polynomial networks. And what we did in this paper, basically, we used Grobner basis techniques to describe, for a given data set, the collection of all the models that fit those data, rather than not enumerating them, but describing them in terms of a Grobner basis, sort of describing the null space of a matrix, not by listing all the elements in that vector space, but by giving a basis of that vector space. So that really was the basic content of this paper. So that that got us started on this polynomial view, which turned out to be actually quite fruitful. So the general definition, the general context is polynomial dynamical systems over finite fields. So that's the mathematical framework that I'll talk about from here on out. And so that gives you, number one, it gives you a lot of theory, it gives you a lot of theorems. One of the things we use, for example, is primary decomposition of ideas. And it gives you, of course, a lot of computation techniques. So for a lot of the computational things we do, we use Macaulay 2. And we work with Mike Stillman, who can, we have an algorithm that takes 2 hours to run, and we give it to Mike, and he makes it run in 2 seconds. So it's been a great approach to this. Now, in terms of our problem, we have not really made any progress because, again, any function can be expressed as a polynomial, so we're still just talking about all set functions. So let me show you some examples of, first of all, one example of how we use polynomial algebra, and that's to this problem of taking a function like this, taking a polynomial dynamical system, in this case a Boolean network, and compute all its steady states. And that's probably the most common application of this that most people will encounter. You build a model, you want to know what are the steady states of this model. The steady states, the way you want to think of them is they correspond to the different phenotypes of the cell. So what is a cell capable of doing? The different steady states will tell you that. That's a concept that goes back to maybe the 70s, to Stuart Kaufman, who introduced Boolean networks as appropriate models for intracellular networks. And so I think you just asked, how do you decide which types of models you use? Right? If you want qualitative answers, then this might be a good modeling framework, especially if you have qualitative information. Right? So if you talk to many experimentalists, they will tell you, well, just this gene goes up and that gene goes down, or it goes up threefold and this goes down fivefold or something like that. Right? People will not tell you if this gene goes up 2.37fold. So what most experimental techniques provide is qualitative insights and qualitative data. So for this sort of thing, this is a good framework to use. And there's just an example, just to make sure we're clear on what I'm talking about. So this would be a polynomial dynamical system over the field with 3 elements and 2 variables. These are 2 polynomials. First one for the first variable, second one for the second one. On the left is the, what you could call dependency graph, or biologists might call it the wiring diagram of your network. And on the right side, you have the state space. It tells you in a given state, it gets mapped into different other states. So this would have 2 components as 2 attractor basins and 2 attractors, both of which are limit cycles of length 2 and 3 respectively. So that's, and the question is, knowing the functions, knowing the left-hand graph, tell me something about the right-hand graph. So here's an example of an algorithm. That's a pretty good algorithm compared to others that are out there right now, that we published a couple of years ago. They compute steady states of Boolean networks. And let me explain how that goes. This is really sort of the outline. You take a Boolean network, a general Boolean network. Then you construct a different Boolean network from that, which uses only the logical operator and not. So you eliminate the or operator. And the way you do that is essentially you introduce 1 extra node for each or operator you have in there. So you actually, first of all, you increase the network in size. And it's basically what you do is you introduce another node using the fact that A or B is logically the same as not A and not B. And that's what you use to get rid of ors. And this representation has the feature that if I know the steady states of G, I can reconstruct the steady states of F. So you change the network, you change the function, you change the number of nodes, but you preserve information about the steady states. Then you do a reduction. And the way you do this reduction is that if you look at a network that only uses the AND and the NOT operator, then all the information about the functions is actually included in the dependency graph. So I just need to look at the graph, and I can immediately reconstruct the network. Okay, and the graph will be a signed graph, so it's plus or minus 1. If I have a plus 1, if I have a minus 1, I use negation. If 2 edges come together, I know that variables are combined by AND. So the graph knows everything. So this reduction from G to H is purely a graph theoretic reduction. You take certain graph theoretic motifs and replaces them by other graph theoretic motifs. Again, which has the property that you preserve all information about the steady states. So H, once you know the steady states of H, you can reconstruct the steady states of F. Then you take H, you turn it into a polynomial system. You solve that polynomial system, you get all the solutions for it, and then you simply work your way backwards to get all the solutions of it. That's
How exactly do you solve it? Or just like it's a framework, so it doesn't matter.
you just use, we call it unit.
Whatever it's there.
Yeah. And so this is the list of graph theoretic motifs. There are 9 such rules. They're totally ad hoc, so we really don't know whether there are others. We don't know. Probably if you apply them in different order, you get different answers. But the way you want to interpret this, and there's really no use in going through all of those, but you can take the right hand, the left hand of each one of these implications and replace it by the right hand, and you will preserve information about steady state. So you can produce, you can go backwards and produce steady state. So there's this substitution going on, and
did I hear you correctly that you said you did not test whether or not you would get the same result if you did the same thing in a different order?
we did not. I would guess they did not. I mean, it seems to me there is some, if one were to think about this carefully, one could probably figure out why this works. So there's some theory behind this, but we simply did this very, very ad hoc. So that's the process. So let me show you an example. So here's an example. This is a published network of an intracellular network of what goes on in a particular type of immune cell. So this has 23 variables, I think, 23 or 24. And so it has 2 to the 24 states. So you could compute this brute force to see what the steady states are. But if you apply this algorithm, the first step would be, that's what you get when you do this and not reduction. So you add a few nodes. You end up with 26 of them, so you add 2 or 3 nodes. And then you do this reduction, and by the time you're done with the reduction, you're left with a network with 2 nodes. And you can compute its steady states. Obviously, turns out there will be 2 steady states. You can trace them back to 2 other steady states. This is a T-cell differentiation network, so there's 2 possible states that this can be. So it's a significant reduction. And here's we tested this and compared it to a number of other algorithms that are out there. So this is a test on several published networks. The second column is the number of nodes in these networks. So you see some of them are 300 nodes, some of them are smaller. And what you see on the right-hand side, you see basically the times. And you can see that, of course, it gets slower. Now, if you notice, the way this is ordered is according to the third column, which is the average in degree of the network. So as the in degree gets up above 5, it becomes very, very slow. And what's slow is to solve systems of polynomial equations, because the in degree tells you how many variables your equation has. So
I'm sorry, you said it's average in here?
Yes. So you take the in degrees of all the nodes. And 5 is not unreasonable. So you could have lots of things that are regulated by that many things. So, and we've compared it to other ones. So it's, I would say, maybe the best algorithm to do this. There are examples where this fails spectacularly. For example, if you have a network that has majority functions on it. So a majority function is a function in a number of Boolean variables, and what you do is it takes on the value 1 if you have more 1s than 0s. It takes on the value 0 if you have more 0s than 1s. And this project I was telling you about earlier about resistance in chemotherapy, the way we construct the networks is majority functions. Because we don't know the details of how the regulation works each one of the cases, and so this totally blows up. So doing just the end node representation gives you a gargantuanly larger network than what you started. So it fails.
So in these tables, you're listing seconds, 10 seconds, right?
Yes.
Do you ever encounter comparison of different methods of rather the as a comparison of formulas like n, e, 2 to the n, and so on, n log n? So do you ever see that as a comparison, or you rather see more frequently comparison just in seconds? What's more appropriate?
Oh, so you mean, well, for all these algorithms, it's very difficult to estimate the complexity.
Do you see any use in estimating the
Oh, any use in estimating the complexity? Well, not really, right? So I tell you, for example, that Grosvenor bases are doubly exponential, right? So I tell you this, and then you say, well, your algorithm uses Grosvenor basis calculation, so forget it. Well, it depends, right? In most cases, it won't be doubly exponential. So from a practical point of view, it's I would say of limited use to know the complexity of a number. And probably most algorithms that people use, certainly in computational biology, have horrific complexity. But you can make them work in many cases. What happens here is, eventually, whatever algorithm you have, the size networks that you care about will totally overwhelm any method that you have. So it's actually of limited use to sort of push this further and further, because ultimately, what you will be forced to do is simply use sampling of the state space. Right? So if you do that, it would be good to have some information about, say, how many states you should sample. If I have n variables, I should sample, say I have 10 variables, I have 2 to the 10 states, or let's say maybe 500 variables. 500 variables. How many states should I sample from the state space? 1 million, 10 million, 100 million? I don't know. It would be useful to have such information, and I'll get to that a little bit later. So this is an example of a very practical thing that we've been working on quite a bit. Is you have a computational problem, you want to have information about a biological system through a model, and this is an algorithm that actually is one of the algorithms that gives you the exact answer, not an approximate. So it's not a heuristic algorithm. Almost all algorithms, I think, that you use in computational biology are heuristic, right? And you end up building heuristic algorithms on top of heuristic algorithms, and at some point you just don't know. And everybody recognizes that problem, I think, but it's difficult to. You can say, well, okay, they're all heuristic algorithms, so it's useless, but you cannot just sort of roll over and die. You need to do something. Right? And if you don't provide some solution to this, somebody else will. So,
by the way, is there a reference 23?
Is there a reference 23?
What's the number? If there is a reference 23. So actually, so the underlying question is, 4,000 seconds is not so many, right? So you can wait that long. So did you experiment to?
I see. Well, so
something larger.
Well, so if you look, so there's this asterisk by this number, okay? And what it says basically is the model that was used has a lot of has some variables that have no inputs, so they're sort of like external parameters. You can choose values for them. And for each value you choose, you get different steady state. And so you have a lot of different initializations. And what the asterisk says is basically we could only do this computation for about half of the initializations. For the other half, it didn't finish. So in this case, no, there's not a 23.
Does it surprise you that it's just like half and half, and not 1% and 99%, sort of something exceptional and not exceptional? Does it surprise you?
Yeah, well, I mean, it's hard to draw any conclusions from one model.
Okay.
One would have to do something a bit
So
more
that
systematic.
model was exceptional in that
It
sense.
could be, I think it could be. I don't even remember what in particular this model is. It's a reasonably large model, so I don't know. So much for computation. So the other track that we've been going on is, well, maybe we can look at different restrictions we could put on these functions. Right? In particular, maybe not any function whatsoever will show up as a rule for a biological entity. Right? Just like when you model things using differential equations, the assumption is that essentially everything looks like Michaelis-Menten or Hill equation, a very, very limited type of differential equation that shows up. So these things are very special. That's the assumption. So what I want to tell you about is one track we've been following, and we've been following it in part because I find it appealing just purely mathematically, and I think it also leads to something useful, hopefully. We started working on this around the same time we did this 2004 paper. We said, okay, now we have these dynamical systems, Boolean network models. So what can we say? What sort of assumptions could we make to make this problem tractable? And coming from computational algebra, if you want to pick special polynomials, the obvious thing you're going to pick is monomials. The first thing you would do. Monomial ideals, you know everything about monomial ideals, easy to do. So that's what we did here. And the problem, the question we asked is, can we characterize all Boolean network systems, Boolean networks consisting of monomials, so that corresponds to Boolean functions that are simply built from the AND operator. That's equivalent. So can we characterize all those that do not have any periodic points, all those that only have fixed points? And it turns out one can. And it was a very nice answer we got. So as I pointed out before, if you only use the AND operator, then your system is completely characterized by the graph, by the dependency graph of this network. So maybe there is a graph theoretic answer to this question. And in fact there is. If you take this dependency graph, how the variables interact with each other, and let me make the assumption that that graph is strongly connected. So between any two nodes you have a directed path. Then I can define a number, which we call the loop number. We could not find this number. Of course, we should have known that there's no new number you can define that's associated to a graph. Somebody has not already defined for you. So in this case, we called it the loop number, which is the greatest common divisor of the lengths of all directed loops. Now, of course, so it's in other places it's known, for example, as the index of impermittivity, and some other places it has shown up. But anyway, so we called it the loop number, and we could show that a Boolean monomial network has only steady states if and only if this loop number is 1. The proof is sort of a not very insightful inclusion-exclusion type combinatorial argument. So we published it in Annals of Combinatorics which is appropriate. But so there was a beautiful answer. And
Is it possible to chain a bunch of networks together that each have loop 1 and have them overall express a steady state?
yeah. So, so of course, the assumption for this is that your network is strongly connected. Okay, so that's a strong assumption. And what we did here is we looked at, well, what happens if it's not strongly connected? Right? Can we sort of glue strongly connected networks together and know something about the loop number of the gluings? And one can say that, so one can give a condition. If I glue together two networks that only have steady states and I glue them in a certain way, then the resulting network is only steady states and things like that. So one could do that. But we picked this up.
Excuse me. Can I ask a question? So, but why is it important to distinguish between only steady states or existing periodic points?
Yeah.
So, like, what's the meaning?
Yeah. So
biological
it's
sense?
well. I mean, so it's biologically interesting because. I mean, so number one, you could look at periodic phenomena, like cell cycle, for example, is periodic. Circadian clocks are periodic. There you're looking for periodic features. But for example, if you have something you know will give you a steady state, and you get a model that has periodic points, then the odds are the model is wrong.
Okay, so it's a way to assess the models.
Yeah.
Okay.
But I must admit, the way we came up with this question was purely like, what kinds of questions could we ask? You know? And of course, the other thing is that monomial systems are biologically not very healthy. They don't show up very much. They show up in some places, but almost all biological systems are not. So it was purely a mathematical exercise.
So it would rather be what kind of questions can we answer?
Yeah. Well, you know, I mean, one approach is I have a hammer and let's look for the nails. You know, which questions can we answer with the framework we have? So we picked this up in 2010. We went back to this loop number business and extended the result. So there the question was really for a given network, so conjunctive, that's the same as monomial, and disjunctive is the same, except using the or operator instead of the and operator. And so there we asked the question, can we actually, for a given system like this, write down all the attractors, all the periodic points, all those steady states, write down exactly the dynamics. And the answer is one can, and it's sort of a very nice answer in the sense that the only periodic points you can get are periodic points of a period that divides the loop number. And here's a closed form formula for the number of periodic points of any period. So for any divisor m of the loop number, I can write down the number of periodic points in terms of the prime factorization of them. Okay. So once I have the number of periodic points, I simply divide by m, and I get the number of periodic attractors of period m for each m. So in particular, if the loop number is 1, then you have no periodic points of period anything other than 1. So that, as a special case, recapitulates the previous result. And so this also has the assumption that the graph is strongly connected. Otherwise, actually, the loop number is not well defined. So you cannot do this. But so then we also looked at non-strongly connected graphs. And what we got was, we got a lower bound, a sharp lower bound, and we got an upper bound. So So given a general Boolean network that's conjunctive, there's a sharp lower bound for all periodic points of a given period, and there's an upper bound that is not sharp. And it's very nice. It's in terms of the antichains in the closed set of strongly connected components. So if you take the graph, you can essentially decompose it into partially ordered set of strongly connected components, and the antichains in this determine what happens in general. So you get upper and lower bounds. So for example, for the problem of sampling the state space to know how many steady states you have, having a lower bound would be very useful, because if your lower bound is 10, if you say, let's say you have a sharp lower bound of 10 and you've only found 5 steady states, then you know that you're missing 5 others, so you better go and look somewhere. And having an upper bound obviously helps as well. So it would give some guidance as to how much you need to sample. And we've recently actually gone back to this, because one question was, well, okay, this works for Boolean networks, so what happens for multi-state systems? And it's a very nice paper that's really almost entirely Alan Feliz-Cuba's work. He's generalized this to a general finite set X, and any semi-lattice operator on X. So if you have a semi-lattice operator on X, so it's an operator that goes from X cross X to X, which is commutative, associative, and idempotent, then then you can write down essentially the exact same formula for the number of periodic points of a period. So a very, very general result, and that actually has a more enlightening proof. It's in terms of sort of generalizing how you would solve this problem for linear operators. So you define a new kind of multiplication of matrices, which actually, with a little bit of work, one can put it into the context of tropical geometry, or the operator, the operations research version of this, the operations research people have done since the 50s with the arithmetic and the max plus algebra. So for for sort of homogeneous systems that are built from one operator, this is sort of an example of how one can completely solve this problem. And of course, the drawback is that that it's a very limited type of framework. So I want to just spend a few minutes, because I want to get to the end, to talk a little bit about what sort of other restrictions that are maybe biologically more useful one could place on functions that would help one solve this problem of understanding dynamics from the functions. What it uses is this concept of canalization in biology that was invented in the 1940s in evolutionary biology. So it's the idea is you look at an embryo, and that embryo develops into a very well-defined organism in pretty much the same way, in a variety of different environmental conditions, a variety of different buffered by a variety of different stochastic features. So there is some force that must channel this embryo into a certain type of development, and so canalization was that force. So it's a little bit like physicists postulating the ether. You don't know what it is. It's some unspecified force that does this, and canalization was this unspecified force that did this. And the way one can picture this is, this is a picture from a book by Conrad Waddington, evolutionary biologist who sort of came up with this concept, is you can think of of development. So you have a cell that's this little ball up there, and it starts out at the beginning of its development, so it's unspecified. It's a stem cell, and it sort of rolls down this landscape, and these valleys are pretty deep, and once it gets down into a valley, you can sort of push it around, but it'll stay in this valley and run all the way to the bottom, and that's a particular waterfall. And the force that shapes this landscape of mountains and valleys, that's canalization. So it's interesting. For a long time, there were really no mechanisms known. In the last 10 or 15 years, actually, there's been quite a bit of interesting developments. But this concept of canalization was taken by, again, Stuart Kaufman, who started this whole Boolean network development in biology, and was adapted to Boolean functions. So he would call a Boolean function canalizing if it has the property that there's one variable, and if it gets a particular input, then it determines what this function does, independent of what any of the other variables do. So an example would be A and B. If A is 0, then that determines what the function A and B is, regardless of the value of B is. So more complex functions, the same applies, and so that's a concept that sort of makes sense. There's some evidence that a lot of the functions that show up in models actually have those properties, and so we and others have worked quite a bit. This was sort of the first paper we did, looking at a special kind of canalizing function. Turned out that these canalizing functions were really well known in other areas. One of the things we did, one of the results in this paper is that you can take these canalizing functions and you can parameterize them by a particular polynomial representation. So you can, in particular, compute how many there are for a given number of variables. So we computed the first so many, and we put that integer sequence into Sloan's integer database. And the match was with a number of unate cascade functions, which electrical engineers and computer scientists have studied quite a bit. They have, one of the features they have is that they give you, when you use them to construct binary decision diagrams, you end up with binary decision diagrams of shortest average values. So they have nice properties. And so that was really the beginning of what a number of people did. Here's the polynomial characterization, but let me not go through this. This is a paper that appeared last year that sort of takes any Boolean function and characterizes it from the point of view of its canalizing properties, so-called canalizing depth, which is the starting point for a project we're doing now. As I said, there's some evidence that the logical rules of actually how gene regulation works, for example, have canalizing features. And in the 90s, there was a study done on some published models that verified this. But in the meantime, there are hundreds of such models that are published. My estimate would be maybe 500, which gives you about, say, 5,000 functions. And so we're starting a project to compute for all of these functions, to compute their canalizing depth, and to categorize sort of, what are really the properties of rules of gene regulation, for example, before we keep pushing this further. So this is an ongoing project. And this is one of the beginning papers of a program to take canalizing functions and see what their effect really on dynamics is. Some robustness features, numbers of steady states, etc. So it goes really toward this this goal of imposing particular particular properties that make this a problem of finding properties of the state space graph more tangible. So let me just take the 1 minute I have and talk about where we want to go from here. And there's a number of different things one could do. I want to, in the short time, I want to just focus on one of them. And that's this idea of getting upper and lower bounds on the number of, say, steady states and periodic attractors, which if you want to compute these things by sampling, which is ultimately going to be the only reasonable way to do this, then you need to have some information about upper and lower bounds. And so how do you do this? Well, my idea is to do a program similar to one that was carried out successfully in group theory, finite group theory. And so of course it is also impossible to find out something about all finite groups. Say, classify all finite groups. So you don't do that, of course, but what you can do, as it turns out, you can use the fact that every finite group has what's called a composition series. So it is a sequence of normal subgroups, so that successive quotients in this composition series are simple. So if you could compute those quotients and you know something about how to put simple groups together, how to combine them, then you know something about all finite groups. And of course that was the monumental team science project in mathematics to classify all finite simple groups. So that is, I think, essentially done, as far as I know. It's monumental. And I'm thinking of a little bit something similar. Right? So, for example, one could think about these. If one uses these monomial systems as an example, and so we know exactly what goes on for monomial systems with strongly connected dependency graph. If I can set up an appropriate framework so I can form essentially the equivalent of quotients of Boolean networks that preserve some properties about the related state spaces, then I could think of a similar sort of thing, some sort of a filtration, that so that each difference essentially, I know something about. The difference is sort of the equivalent of a simple group. And I know how to sort of put these things together, not in terms of exact numbers of steady states, but in terms of bounds, upper and lower bounds. And that would actually be of great practical usefulness, I think, if one could do this. So that's one of the things that I would like to pursue. I don't have any concrete ideas. But a lot of the things we've done sort of were motivated by that thought of a bigger program. And I think at this point I will stop just saying that, thank you to our sponsors. So thanks for your patience. Any questions? I'm happy to answer.
So, assume that we have this dynamic system that we know that all these functions are canalizing or small canalizing depth. Are there any algorithms that can benefit from this knowledge? Or?
I'm not sure I understand your question.
Okay, assume that I know that functions defined dynamic system are in some sense canalizing. Okay?
Mm-hmm.
So, is it true that I can have, there are better algorithms for finding also steady states than for general case?
Well, so that's precisely what we've started to do in this paper here, is to see if we have, so there are certainly many simulations. People have simulated networks with canalizing functions. They have fewer steady states, they have fewer attractors, they have more robust perturbations, things of that sort. But these are all simulation results. So what we've been trying to do is derive tools, like here, for example, one of the tools we derived is you can measure the robustness of a network. One of the ways in which you measure the robustness of a network is if you have a state, and you perturb the state by flipping one component. So you go Hamming distance 1, and then you track these two states. And you see what happens. Do they diverge? Do they converge? So how does a small perturbation propagate? So there's something called the Derrida value that you can compute, especially for. I'm sorry?
What was it called?
The Derrida value, D-E-R-I-I-D-A. And so that you do by simulation, basically. And so for larger networks, it doesn't really work to compute it. And so one of the things we have in here is a closed form formula that is very, very simple to compute. So it's very easy to compute for a given network what its robustness is. Things of that sort.
Okay.
So I don't have any specific results to give you, because I don't know of any other than the things derived by simulation. Thanks so much.
Thank you.
Thank you.